1, 2, 3, 4, 5, 6. 6 carbons. It is a hexane. When hexane treated with Cr2O3, Al2O3, 773 Kelvin, 10 to 20 atmosphere. So here not only Cr2O3, we can also use V2O5, we can also use MO2O5. In place of Cr2O3, we can use V2O5, MO2O3, MO2O3. This reaction is known as aromatization. This reaction is known as aromatization and also called reforming. So here minimum 6 carbons are present. It will be converted into benzene. 1, 2, 3, 4, 5, 6. Ring closing and benzene will form finally. Now the benzene is treated with ozone, zinc and acetic acid. So this is the reductive ozonolysis reagents. Reductive ozonolysis. So here benzene undergo ozonolysis because no other functional group is present, and finally it gives 3 moles of glyoxal. 3 moles of glyoxal. Now it is treated with calcium hydroxide and heat. It is a aldehyde without alpha proton, aldehyde without alpha proton. So aldehyde without alpha proton treated with the base, therefore it is a Cannizzaro reaction. And of course within the same molecule we are having 2 CHO groups, therefore it is a intra-Cannizzaro reaction. Therefore in intra-Cannizzaro, if OH minus attack on the aldehyde carbon, that carbon undergo oxidation and remaining carbon undergo reduction. OH minus attack on the carbon, that carbon undergo oxidation, remaining carbon undergo reduction. So it is a Cannizzaro reaction product. One, two, three, four, five, six, 7. It is a heptane. Heptane treated with V2O5, Al2O3. So here not only V2O5, we can also use Cr2O3. We can also use MO2O3. 773 Kelvin, 10 to 20 atmospheric pressure. This reaction is known as aromatization and also called reforming. So if minimum 6 carbons are present, it undergo first cyclization and finally it converts into, initially it undergoes cyclization and finally it converts into benzene type compound. So finally we got toluene. So this reaction is known as aromatization. Now it is treated with CrO3 and acetic anhydride. CrO3 and acetic anhydride. So here the benzylic carbon replaced with corresponding ester group. And this ester group is coming from acetic anhydride. So this is called benzylidene diacetate. It is a benzylic carbon. So benzylidene diacetate. Now it is treated with H2O and we are heating at room temperature. And this ester undergo hydrolysis. This is the only possibility we have left. So here H2O attack and here H2O attack. Therefore finally it gives corresponding product CH, OH and corresponding acid OH and corresponding carboxylic acid. If the same carbon having the two OH groups, that is called hydrate, and that hydrate is unstable, immediately loses water and finally converts into benzaldehyde. So this is benzaldehyde preparation according to NCERT. This entire reaction is benzaldehyde preparation from NCERT. Alkane treated with AlCl3 and HCl. So it is a Lewis acid. So when alkane is given in the presence of Lewis acid, this reaction is isomerization. So one alkane undergo isomerization produces another alkane. So here 4 carbon chain. If it undergo isomerization, we get 3 carbon chain and 1 carbon left. So we get finally isobutane. It is also alkane. Now isobutane treated with KMnO4 at 0 degrees Celsius. So generally alkanes do not undergo oxidation, but alkanes having tertiary hydrogen, and the tertiary hydrogen undergo oxidation, the tertiary carbon hydrogen undergo oxidation, finally you get corresponding tertiary alcohol, and this compound is tertiary butyl alcohol. Now the tertiary butyl alcohol treated with silver and heat is 300 degrees Celsius. Not only silver, we can also use copper and we can also use gold. And we know that primary alcohol undergo oxidation, gives aldehyde in the presence of these reagents. Secondary alcohol undergo oxidation and gives corresponding ketone, and tertiary alcohol undergo dehydration, finally it gives corresponding alkene. So in this case also, this tertiary alcohol undergo dehydration, finally we get corresponding alkene. So this is called dehydration. This reaction is dehydration, and the product is called isobutene. Methyl cyclopentane treated with Br2HNO. So this is alkane treated with Br2HNO. It is a free radical substitution, and bromination is highly selective because reactivity order tertiary, secondary, primary, reactivity order 1600 is to 82:1 approximately. That means primary carbon reactive, for example, 1 time, and secondary carbon 82 times more reactive than primary. Tertiary carbon 1600 times more reactive than secondary and primary. That's why here first we think about the stable radical in the entire carbon chain. It is a stable radical. Now the stable radical react with Br2. Finally we get corresponding tertiary bromide. So this is the alkyl halide. Now this alkyl halide treated with alcoholic KOH. And alcoholic KOH is a strong base. When alkyl halide treated with a strong base, the reaction is elimination. Majorly elimination. In the elimination, first we think about E1CB, but in the given compound alpha, beta, at beta position there is no minus R, therefore E1CB not possible. now we should think about E2. Now in the E2 we are having the condition good leaving group and less bulky base. Good leaving group and less bulky base. It gives corresponding CHF alkene. It gives corresponding CHF alkene as a major product. Therefore, by removal of HBr, we get these two compounds. Now, first one is Hoffman alkene. Second one is CHF alkene. CHF alkene. And CHF alkene is major in this case. Now it is treated with benzene and AlCl3. So in organic chemistry, whenever Lewis acid is given, we can consider simply H plus. We can consider simply H plus. Therefore, the major product I am taking here react with alkene and gives corresponding stable C plus, and it is electrophile, and here we are having benzene. Therefore, it undergo Friedel-Crafts alkylation. It undergo Friedel-Crafts alkylation. Therefore, finally we get corresponding Friedel-Crafts alkylated product. So it is our electrophile and it is our aromatic compound. This is a Friedel-Crafts alkylation. First one is free radical substitution. Second one is elimination. Third one is electrophilic aromatic substitution. Alkane treated with copper and O2, 523 Kelvin and 100 atm. So this reaction is free radical substitution. So in this reaction, the carbon undergo free radical substitution and finally we get CH3, CH2, OH. So this reaction from alkanes from NCERT point of view, it is a free radical substitution. Now it is a ethyl alcohol. Ethyl alcohol. When ethyl alcohol treated with H2SO4 140 degrees Celsius, and we have another reaction from NCERT, H2SO4 at 180 degrees Celsius. So here 313 Kelvin and here 353 Kelvin. So at 140 degrees Celsius, SN2 reaction takes place because both are primary alcohols. Finally, we get corresponding ether as major product. At low temperature, substitution major. But 180 degrees Celsius is high temperature for this reaction. It undergo E2 dehydration, alpha, beta, and it gives corresponding alkene. So this reaction from NCERT. Ethanol, low temperature substitution, high temperature elimination. Now this ether treated with excess of Hi. So lone pair attract the proton and gives corresponding oxonium ion. Now the I minus attack on the primary carbon, leaving group will leave. So it is a SN2 reaction and it gives corresponding primary alcohol and primary iodide. Again it reacts with Ha because in the question it is mentioned as excess. Therefore it produces corresponding oxonium ion. Now this I minus attack, leaving group will leave. Finally we get corresponding alkyl iodide. So this is our final product. So this is simply ether cleavage in the presence of Hi. Ether cleavage in the presence of Hi. Because both are primary, we observe the SN2 mechanism. Alkene treated with H2 triphenylphosphine rhodium chloride. It is called Wilkinson catalyst. Wilkinson catalyst. So it is simply hydrogenation reaction undergoes syn addition. So here cis alkene undergoes syn addition. Finally it gives corresponding N-butane. N-butane. Now the N-butane treated with MO2O3 heat. N-butane treated with MO2O3 heat. So from NCERT point of view, alkane undergo oxidation, and here the terminal alkane undergo oxidation. Finally we get corresponding aldehyde. Aldehyde treated with aromatic compound in the presence of H plus. So initially ketone attract with H plus. It gives corresponding, it is a butane, oxonium ion, breaking of pi bond, and produces electrophile C plus. Now this electrophile attack on the benzene, and we get corresponding aromatic compound, and it is our electrophile. But we are conducting reaction in acidic medium, that's why it loses again H2O and produces electrophile. Now the electrophile reacts with another benzene, and finally we get corresponding product like this. So it is a benzene, and it is a aldehyde. So it is simply electrophilic aromatic substitution. So similar reaction, CCl3CHO treated with chlorobenzene. So in this case also, in the presence of H plus, 2 moles granted. So undergo at para position electrophilic aromatic substitution. That means whenever aldehyde or ketone treated with aromatic compound, 2 times electrophilic aromatic substitution granted. So this product name is DDT. It is an alkyl halide. Alkyl halide treated with zinc dilute HCl. We can also use zinc acetic acid. So it is from NCERT. So from NCERT it is very clear that alkyl chloride, alkyl bromide, alkyl iodide, when treated with this reagent, it undergo reduction and finally it produces alkane. Similarly, when alkyl fluoride treated with the same reagents, there is no reaction. So this reaction from NCERT. Therefore, here the corresponding chloro will be reduced and fluorine carbon cannot be reduced. That's why the corresponding product is like this. So chlorine connected carbon is reduced. Now it is treated with Br2H nu. So we expect free radical substitution. So we focus on the stable radical, and here bridge carbon, even though it looks stable, but here if the radical is formed at bridge carbon, hyperconjugation not possible. Bridge carbon, suppose radical is formed, and this hyperconjugation not possible. That's why I am taking the stable radical in the given compound here, because it is having one hyperconjugation. Of course, we expect this radical also, but we know that if already halogen is present at the same carbon, radical will not be preferred majorly. If other possibility is not there, then it can possible, but other possibility is there. That's why we should not consider this one. So it forms stable radical, and stable radical react with Br2. Finally, it produces corresponding bromine and fluorine. Now it is treated with alcoholic KOH. It is a strong base. Therefore, we expect elimination. And we expect first even CB mechanism, but beta position no minus R. Suppose with respect to Br, it is beta position no minus R. With respect to fluorine, it is beta position no minus R. Now we will take E2 mechanism, and if good leaving and bad leaving both are competing, we should remove the good leaving. If good leaving and bad leaving both are competing, we have to remove the good leaving. Therefore, with respect to Br, alpha carbon and beta carbon, so we have to do elimination. And finally, we get product like this. Now, if it undergo further elimination, it is alpha, it is beta, and it is beta. If it undergo further elimination, either this product or this product should be formed. But both are not possible because 6-membered ring, sp carbon not possible, bridge carbon, sp2 carbon not possible. That's why here further elimination not possible. It is our final product because the geometry not supporting for further elimination. Alkyl chloride treated with sodium and ether. So this reaction is known as Woods reaction. So in Woods reaction, what we do, we remove the halogens and write down the C radicals, and within the molecule 2 radicals are present. Therefore, the final compound is alkene. It is a Woods reaction. Now, the alkene treated with cold alkaline KMnO4, it is called Bayer's reagent. It is called Bayer's reagent, and this reaction is syn hydroxylation. This reaction is syn hydroxylation. Therefore, at this double bond carbon, we have to add simply 2 OH groups. Both are cis, both are above the plane cis, and both are below the plane cis. Of course, these two molecules are same if I rotate the molecule about this axis. Now, it is treated with H2SO4. So, this compound is pinochle type. Of course, even if you are not finding the, if you are not recollecting the pinochle compound, no problem. Simply follow the mechanism. In the presence of H plus, loses H2O. In the presence of H plus, loses H2O and form stable C plus. Now here ring contraction takes place because the only possibility ring contraction here. Why it is undergoing ring contraction? Because here octet is possible. So for octet, ring expansion, ring contraction, anything is possible. So here for getting octet, ring contraction takes place, and finally we convert this compound into like this. Now we have to remove the proton and it converts into ketone. So this entire reaction is known as pinochle-pinocholone reaction. The product is called pinocholone. Since it is a pinochle, the related product should be called pinocholone. So this entire reaction is pinochle-pinocolone reaction. Alpha bromo beta bromo, not alpha bromo, alpha beta bromo carboxylic acid. The reactant is. It is treated with soda lime. It is treated with the soda lime. When soda lime treated with the carboxylic acid, this reaction is decarboxylation. So decarboxylation. So what we have to do? We have to remove the CO2 and write down carbon ion. And this carbon ion converts into finally alkene. So in this case, the structure supporting for alkene formation. జనరలీ డీకార్బాక్సిలేషన్ ఆల్కేన్ ఫామ్ అవుద్ది, బట్ ఇక్కడ స్ట్రక్చర్ని బట్టి మనం తీసుకోవాలి కాబట్టి ఫస్ట్ C- ఫామ్ చేయాలి. అండ్ C- అనేది లీవింగ్ గ్రూప్ని రిమూవ్ చేసి కరస్పాండింగ్ ఆల్కేన్ ఫామ్ చేస్తుంది. నౌ ఇట్ ఈస్ ట్రీటెడ్ విత్ NBS and HNO. So it is a free radical substitution. NBS always contains some amount of impurity Br2, and NBS means N-bromosuccinimide. 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 So it undergo free radical substitution, and NBS specialty is only at allylic and benzylic carbons. The plus R group should be connected to corresponding radical. So here it is a allylic carbon, it is a allylic carbon, both are same here. Therefore I am taking double bond allylic carbon. Now it react with NBS. Finally we get corresponding allylic bromide. Now the third reaction is, it is a aromatic chloride, aryl chloride. It is aliphatic. Aromatic alkyl halide, aliphatic alkyl halide treated with the sodium. So this reaction is Wurtz-Fittig reaction. If both are aliphatic, Wurtz reaction. Both are aromatic, Fittig reaction. One aliphatic, one aromatic, Wurtz-Fittig reaction. So in this case, this product is possible, this product is also possible, and finally the major product and cross product, this is also possible. AA, BB, AB. So it is our Wurtz-Fittig product. So generally cross product is major. Alkane treated with O2 and MO2O3. So from NCERT point of view, the terminal carbon undergo oxidation and it gives corresponding aldehyde. But in the given question, the reagent is not MO2O3, O2, and the reagent is manganese acetate. So from NCERT point of view, the terminal carbon undergo oxidation, it gives corresponding carboxylic acid. So now it is treated with NaOH. When carboxylic acid treated with NaOH, here acidic proton, here hydroxyl group, acid base reaction takes place, and corresponding sodium acetate will form. Sodium acetate. Now sodium acetate electrolysis, this reaction also known as cold base electrolysis. So in the cold base electrolysis, we have to remove the CO2 and we have to write down the radical, and the radical dimerizes. Finally it converts into alkane plus CO2. These two products at anode, and at cathode NaOH plus H2. These two products at cathode. At anode oxidation, at cathode reduction. So this is a cold base electrolysis. Alkyne treated with sodium liquid ammonia. This reaction is known as Birch reduction. It is a Birch reduction. So in the Birch reduction, the alkyne will be converted into alkene, but here we get only transalkene. When the transalkene treated with Br2, so here anti-addition possible, but plus R group is there. Therefore alkene react with Br2, and even though it forms initially 3-membered ring, but because of plus R, ring opening takes place. So corresponding carbocation is formed, Now here Br minus attack from the Br2, both from above the plane and from the below the plane. Suppose it is a syn addition type and it is an anti-addition. So because of formation of C plus, here syn plus anti both are possible, but anti-addition dominates. Anti-addition dominates. That's why we get corresponding product finally, dibromo product. Dibromo product. So one of the dibromo product is like this: PH, CH3, hydrogen, hydrogen, Br, Br. Suppose it is syn addition type compound, PH, CH3, hydrogen, hydrogen, Br, Br. It is a anti-addition type of product. So this reaction is simply halogenation. Alkene reaction with Br2. This reaction is halogenation. Halogenation. Now it is treated with zinc and heat. So 1,2 dibromo compound, 1,2 dibromo compound treated with zinc. So here simply we have to do anti-elimination. So when it is treated with the zinc, it is treated with the zinc. So we have to do anti-elimination. So to do anti-elimination, so first what we have to do, we have to convert the structure into Fischer projection. It is a Fischer projection. Now in the Fischer projection, we have to take 2 bromine opposite side. So here we have to remove the halogen Br2, and finally we will write corresponding alkene. So this is an anti-elimination, and finally we get corresponding trans alkene. So from meso compound, anti-elimination, we get corresponding trans. Now it is a racemic type of compound. CH3, PH, bromine, hydrogen, hydrogen, bromine. Now here bromine, bromine opposite side, hydrogen, PH, hydrogen, CH3. So we have to remove the 2 halogens, and finally we get corresponding cis alkene. Corresponding cis alkene. So here it is a racemic type of compound, or simply you can say trio type of compound. It is a trio type of compound. So trio type of compound, anti-elimination, we got cis isomer. So we can remember like this. Suppose if these two are the leaving groups, it is a erythrotype, and these two are the leaving groups, it is triotype. Suppose it undergoing anti-elimination, we get corresponding trans alkene. Suppose trio compound undergo anti-elimination, we get corresponding cis alkene. So this point you can remember for further reactions. So in the given question, the first reaction is Birch reduction. Trans alkene will be the major product, will be the only product. And next one is alkene treated with Br2CCl4, halogenation. And next one is vicinal dibromo compound treated with the zinc, anti-elimination. Here not only zinc, we can also use magnesium, we can also use I minus acetone. So we can use any one of these reagent. And another point, terminal alkynes with sodium ammonia, only acid base reaction takes place, no reduction. Terminal alkyne with the sodium liquid ammonia, there is no reduction, only acid base reaction. The alcohol treated with concentrated sulfuric acid. So alcohol undi, alkene undi. We know that lone pair react faster with H plus. Therefore, initially it forms corresponding oxonium ion. It loses a proton and form corresponding carbocation. Now here elimination not possible because sp2 carbon do not lose the proton. So here another possibility is because of resonance we get corresponding alkene like this, and in the resultant compound undergo ring expansion. The resultant compound undergo ring expansion, we get finally carbocation. Now this carbocation undergo elimination and finally we get corresponding aromatic product. It is our aromatic product. So this is the first compound. We got our aromatic compound. Now it is treated with selenium and heat. Not only selenium, we can also use platinum, we can also use palladium. So it is called aromatization. Aromatization. So non-aromatic ring will be converted into aromatic ring. So finally we get corresponding naphthalene. Finally we get corresponding naphthalene. So non-aromatic ring undergo oxidation by losing hydrogen and finally it converts into aromatic compound. Now it is treated with concentrated sulfuric acid 140 degrees Celsius, concentrated sulfuric acid 180 degrees Celsius. Concentrated sulfuric acid 140 degrees Celsius, concentrated sulfuric acid 180 degrees Celsius. Therefore, alpha position electrophile and beta position electrophile. So low temperature alpha position electrophile, high temperature beta position electrophile. So this is a sulfonation reaction. The first reaction is dehydration. Second reaction is aromatization. And third reaction is sulfonation. Sulfonation. And it is simply electrophilic aromatic substitution and the electrophile is SO3. In the sulfonation, electrophile is SO3 and sulfonation is always reversible. Sulfonation is always reversible. Alkene treated with H2PD. You can use palladium, platinum, nickel, Raney nickel, like that. So this reaction is catalytic hydrogenation. This reaction is catalytic hydrogenation. And we know that in this case we are using only one equivalent. Therefore, we know that rate of reaction indirectly proportional to steric factor. Therefore, this alkene will be reduced and finally we get corresponding product like this. And here syn addition takes place. Of course, it is not chiral center. It is not chiral center. That's why I am not adding the stereochemistry. This overall reaction is syn addition and the reaction is high exothermic heat of hydrogenation directly proportional to number of pi bonds, indirectly proportional to stability of isomer, directly proportional to number of pi bonds, and indirectly proportional to number of isomers, and indirectly proportional to stability of alkene. Stability of alkene. Now, alkene treated with NBS. NBS always contains some impurity Br2. NBS is N-bromosuccinimide. N-bromosuccinimide, and it prefers free radical substitution and mainly at allylic and benzylic radicals, plus or group connected carbon radical. So mainly this type of radical will be preferred. Even minus R also. Minus R radical, because radical can be stabilized by plus R as well as minus R. In this case, alkene is present. Therefore, radical, 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 radical. 4 possibilities are there. Among those 4, these 2 are stable radicals and both are same. That's why I am writing corresponding stable radical. And of course, once a radical is formed, resonance is also possible. So because of resonance, we get another. Therefore, the corresponding product is Br, and the corresponding product is Br. At allylic carbon radical, allylic carbon radical. Now, among these two, the major product is generally stable alkene, because here double bond connected to more number of substituents. Now, this major product treated with the cold concentrated sulfuric acid. Cold concentrated sulfuric acid. It is a cold condition. In the cold condition, simply what happens, alkene react with H plus and form stable C plus, and the stable C plus react with HSO4 minus, and finally we get corresponding S43H. Finally, we get corresponding S43H. Simply electrophilic addition. This overall reaction is electrophilic addition. So when we have to consider this sulfur as a nucleophile, in the cold condition only. So cold concentrated H2SO4. It is useful because some of the functional group react with this compound and those compounds are soluble. And alkene soluble in cold concentrated sulfuric acid, alkyne and ether and aldehyde ketones. Alkene, alkyne, ether and aldehyde ketones. So these type of functional groups are soluble in cold concentrated sulfuric acid. Okay, the first one catalytic hydrogenation, second one free radical substitution, and third one electrophilic addition. Alkene treated with cold alkaline KMnO4, one equivalent only. This is also known as Bayer's reagent. So this is a syn hydroxylation. It is a syn hydroxylation, of course electrophilic addition. Syn hydroxylation, and syn hydroxylation always prefers less sterically hindered alkene. Therefore, the corresponding product is OH above the plane, OH above the plane, OH below the plane, OH below the plane. Suppose if I add excess, another alkene also will react, but here I have mentioned one equivalent. Now, of course, about the sigma bond, if we rotate, same, both compounds are same. Now it is treated with KMnO4 heat. Heat is given. When heat is given, it was 1,2-diol also undergo oxidation, alkene also undergo oxidation. Therefore the alkene part keto and the alcohol part acid. Similarly second one also alkene part keto, alcohol part acid. So when you are heating, here this bond also will break and this bond also will break. But here heat is given, and if you observe this carboxylic acid alpha, beta, gamma. So whenever the tautomeric compound is present, so here tautomeric group, so remove the CO2 directly, or simply you can write like this. First we write like this, alpha beta double bond and beta gamma OH. Now it undergo tautomerization. Finally we get ketone. Similarly this compound also it give the ketone. So you get the same type of same molecule. The molecule is acetone. The molecule is acetone. It is simply decarboxylation. Alpha, beta, gamma. So beta, gamma unsaturated acids undergo decarboxylation on heating. Now the product acetone treated with concentrated sulfuric acid. Concentrated sulfuric acid. So it is a memory based reaction. So 3 moles of aldehyde ketone participate in the reaction. Aldol condensation, aldol condensation, aldol condensation. Therefore finally we get corresponding 1,3,5 trimethyl benzene and also known as mesitylene. Also known as mesitylene. The first reaction is syn hydroxylation with Bayer's reagent. Second reaction is oxidation with KMnO4, and third reaction is aldol condensation. Here MnO2 is present in the entire organic chemistry when MnO2 is used. So according to our syllabus we have oxidation, and the specialty of MnO2 is it oxidizes only allylic and benzylic alcohols. Allylic and benzylic alcohol. So it is a allylic alcohol, double bond next carbon is allylic. Therefore only allylic alcohol undergo oxidation. Only allylic alcohol undergo oxidation. Now the resultant product is treated with the PCC. PCC is pyridinium chlorochromate. It is a pyridinium chlorochromate. It is a PCC. So here the solvent is non-polar solvent is granted. So here we know that double bond PCC will not affect the double bond. So therefore the corresponding secondary alcohol undergo oxidation and produces ketone. For this oxidation we cannot use KMnO4 and K2Cr2O7. K2Cr2O7, because these reagents not only oxidize alcohol, they also oxidize alkene. That's why we cannot use KMnO4 and K2Cr2O7. Now the product is treated with NaOI. NaOI means I2 plus OH minus. So this is a iodoform reagent. Iodoform reaction reagents. So now the reactant has active methylene. So you have to identify immediately. Active methylene connected to two ketones. Therefore it undergo iodoform reaction, COO minus, CH3COO minus, and this active methylene carbon converts into iodoform. This active methylene carbon converts into iodoform. Alkene treated with Br2. So alkene react with Br2 and form cyclic 3-membered ring, cyclic halonium ion. Now the cyclic halonium ion undergo intramolecular substitution reaction. Therefore finally we get corresponding product like this. 1, 2, 3, 4, 5. 5-membered ring. The product is treated with NBS. NBS always contains some impurity Br2. NBS means N-bromosuccinimide. NBS means N-bromosuccinimide. N-bromosuccinimide, and it prefers free radical substitution mainly at if plus R group connected to carbon radical and minus R group connected to carbon radical. So only these kind of radicals are possible, especially allylic and benzylic. Of course, here it is a plus R group, therefore here radical possibility and here radical possibility. So therefore among these two we get two types of radical. One radical like this, and another radical like this. But it is little bit difficult to compare the stability. That's why I am taking two products. It is difficult to compare the stability. That's why I am taking the two products. Okay, generally this kind of questions won't come in the IIT because I have created the question for learning purpose. So that's why it is very difficult in this case. Now here it is treated with NaI acetone. Now here we are having interesting reaction. So it is a 1,2-dibromo. When 1,2-dibromo treated with NaI acetone, it is E2 type of reaction. Therefore, I minus attack, Br will leave, Br will leave. Therefore, we get corresponding alkene. So this one you have to consider whenever 1,2-dibromo compound is present. But here elimination not possible. Here possibility is SN2 type of reaction. In the presence of acetone, SN2. This reaction is Finkelstein reaction. This reaction is Finkelstein reaction. And Finkelstein reaction, SN2 reaction. And this reaction is happening because I minus is good leaving and good nucleophile. And the reaction mainly happening because of polar aprotic solvent acetone. And here SN2 competition. Both are secondary carbons. But this is like if I compare rate of SN2, ROCH2X more reactive than ROCH2X, more reactive than RNH, RNHCH2X, sorry, ROCH2X. ROCH2X more reactive than RNHCH2X, more reactive than PHCH2X, more reactive than CH3X, more reactive than primary halide, more reactive than primary, secondary, tertiary. It is a rate of SN2. So here if I compare secondary and ROCH2X, so ROCH2X is more reactive. That's why this reaction possible, this reaction not possible. If I take one equivalent, therefore the final product is this one. So that's why because of elimination it is a product, and because of substitution it is a product. Alkene treated with HBr. So when alkene treated with HBr, alkene undergo electrophilic addition. So alkene react with H plus and form stable C plus. Now it undergo ring expansion. And form stable carbocation. If I write the structure clearly, 6-membered ring, methyl, methyl, positive. Now we have to add the corresponding bromine. So it is electrophilic addition. So that's why the first product is tertiary bromide. So it is a alkyl halide. Alkyl halide treated with tertiary butoxide, it is a bulky base. Bulky base. So it is a alkyl halide. That's why we expect elimination. Of course, here E1CB not present because alpha, beta no minus R, beta no minus R, beta no proton at all. So here two beta positions are there but no E1CB condition. Now E2, in the E2 we are having bulky base and good leaving. Bulky base and good leaving, we have to focus on the most acidic proton. Generally primary, secondary, tertiary. If resonance concept is not there, primary, secondary, tertiary. That's why here we get two types of products. One product is like this, another product is like this. But we know that this is most acidic proton, it is less acidic proton related, and first one is double bond connected to less number of substance, therefore first alkene is Hofmann, second alkene is Sadjeff. First alkene is Hofmann, second alkene is Sadjeff, and Hofmann is major. Hofmann is a major. Now alkene treated with HCl and peroxide. So even though peroxide is present, HCl do not undergo free radical addition. It undergo electrophilic addition only because HCl bond enthalpy little bit high when compared to HBr bond enthalpy. When compared to HBr, HCl bond enthalpy is high. So that's why HCl do not prefer free radical addition. It prefer only electrophilic addition even though peroxide is present. Therefore, it react with H plus, stable C plus will form, no migration ring expansion. Finally, it react with Cl minus and the corresponding alkyl chloride is major product. Alkene carboxylic acid, both function groups are there. It is treated with I2 and sodium bicarbonate. So one thing we know that sodium bicarbonate remove the proton from the acid. So definitely the first reaction is acid base because acid base reaction is fast. Now it reacts with I2. So initially it forms 3-membered ring and another I minus. Whatever the leaving group is there, that I minus do not prefer attack because we know that if it attack, it forms 1,2-diiodo compound and 1,2-diiodo compound is unstable. Immediately it loses I2. That's why I am not attacking I2. We know that alkene with I2, even though we expect this kind of reaction, it is unstable. Immediately it converts into alkene. That means overall no reaction. That's why I minus is not attacking. But here ring closing possible intramolecular. So this kind of reaction is possible. This kind of reaction is possible. So this is simply electrophilic addition. This is simply electrophilic addition. Now it is treated with alcoholic KOH. So alcoholic KOH is a strong base. So we think about elimination. So it is alpha carbon, beta carbon, beta carbon. So here at beta position no minus R, therefore E1CB not possible. And here we expect only E2, and here we are having less bulky base and good leaving group, less bulky base and good leaving group. Therefore we get mainly Sadjeff alkene. We get mainly Sadjeff alkene. But here in this case conjugation is present. Whenever the conjugation is present, don't bother about the Sadjeff and Hofmann, simply write down conjugation. Conjugate alkene form అయ్యే ఛాన్స్ ఉంటే కాంజుగేట్ ఆల్కీన్నే ఫామ్ చేయాలి. It is a major product. Now it is treated with HBr and peroxide. We know that HBr in the presence of peroxide, it is a benzoyl peroxide. PH, C double bond O, C double bond O, PH. It is a benzoyl peroxide. It undergo free radical addition. That means from this initially Br radical will generate and Br radical attack on the alkene and form stable radical. And we know that radical can be stabilized by plus R and a radical also can be stabilized by minus R. So most stable radical when compared to minus R, plus R radical is more stable. That's why here plus R connected radical is forming majorly. This is a stable radical supporting by plus R and plus H. Now it by the addition of Br, it is a stable radical. Now it will take the hydrogen from the HBr in the propagation step, and finally we get corresponding product like this. It is our final product. The first reaction is electrophilic addition, second reaction is E2 elimination, and third one is free radical addition. Alkene treated with mercury related compound. So here it is a oxymercuration. So in the oxymercuration, initially electrophile form 3-membered ring. So alkene attack aithe leaving group వెళ్ళిపోతే, so corresponding 3-membered ring is like this. It is a oxymercuration. Now intramolecular nucleophilic substitution, and finally we get corresponding product like this. Intramolecular nucleophilic substitution. Now it undergo free radical substitution with NaBH4, free radical substitution with NaBH4, and finally we get corresponding product like this. And here hydrogen is added, mercury and ACOH. So this overall reaction is intramolecular oxymercuration demercuration. So this is our product. Now this product treated with one equivalent HI. So lone pair attract the proton and form corresponding oxonium ion. It is a primary carbon, it is a secondary carbon. Therefore it undergo SN1 type of reaction. The carbocation is formed by leaving the leaving group, and finally I minus attack, and it is our product. So the product is this one. One carbon extra. Here also one carbon extra. So this is our final compound, second compound. Now it is treated with only one equivalent of sodium. So whenever we are using the metal, so here acidic proton is present and here Woods reaction is present, but acidic proton is first preference. Therefore alcohol treated with the sodium gives corresponding alkoxide. So alcohol loses the proton in the presence of metal. Now if you see the final product here, it is a leaving group and it is a nucleophile. Therefore this reaction is like similar to RO minus plus RX. RO minus plus RX. If it undergo SN2, this is called Williamson ether synthesis. Similarly this one also intra Williamson ether synthesis. Therefore the final product is like this, intramolecular SN2 Williamson ether synthesis. The first reaction is oxymercuration demercuration, second reaction is ether cleavage with HI, third reaction is first acid base and then Williamson ether synthesis. Alkene treated with excess of HI. Of course, iodine also there, but we know that iodine and HI no reaction in this case. So alkene react with HI. So initially it produces stable C plus, and the stable C plus converts into by attacking of iodine like this 1,2-diiodo compound. Now the problem is we know that 1,2-diiodo compound is unstable. Immediately it loses I2 and forms alkene. Now we know that excess of HI is given. Again this alkene react with HI, produces stable C plus, and the stable C plus react with I minus. Finally alkyl iodide will be formed. So finally we got isopropyl iodide. Isopropyl iodide. And the reactant is here allyl iodide. Allyl iodide. Now it is treated with the sodium and ether. Isopropyl iodide, sodium. This is a Woods reaction. So Woods reaction, first we form radical and radical dimerase. Radical dimerase. It is a Woods reaction. Now the alkane, the resultant alkane treated with Cl2H. It is a free radical substitution, and when compared to bromine, chlorine is not selective. It is highly reactive when compared to bromine. And reactivity value primary, secondary, tertiary 1:3.8:5. So we have to do the calculation here because the reactivity value difference is very small. So we get one product like this and we get one product like this. So to get this product we are having two hydrogens, these two hydrogens, therefore two hydrogens, and since it is a tertiary carbon, reactivity value 5. Now to get this kind of product we are having total 4 carbons. So these 4 carbons having 12 hydrogens. If you replace any one of these hydrogen, you will get the same compound, 12 hydrogens, and reactivity value, since it is a primary carbon, 1. Therefore the total value 2 5s are 10, 22, 12, 22. So 22 total value. This is a total value into 100. This is a number of hydrogen. It is a reactivity value upon total sum of these two. It is a number of hydrogens. It is a reactivity value, and by calculation we can understand it is a major product. Therefore in this case we are getting primary chloride as major. So in the alkanes case we have to do this kind of calculation because chlorine reactive, not selective. But for bromination directly we can say, without calculation we can say tertiary is major because bromination is selective. That's why selectively it prefers tertiary carbon and then secondary carbon. So it is a free radical substitution. First reaction is electrophilic addition, but it involves 1,2-diiodo compound elimination. Next one is Woods reaction through free radical substitution. Next one is chlorination through free radical substitution. So rate of halogenation, F2 greater than, Cl2 greater than, Br2 greater than I2. Rate of halogenation with alkanes, in case question adigite, fluorine greater than, chlorine greater than, bromine greater than iodine.